Let's add a couple more models to this example of 1D flow. We've seen a one-dimensional model and a two-dimensional model. It was actually symmetric. And so now we'll put in a 3D model. It'll still be the same analysis, but we'll make it full 3D geometry. And so what I did, just for the sake of time, is inserted another model here. And if I expand it, the definitions are already here, just like we did last time. And the geometry I've already built over here. And you can see that it's two geometric entities. I inserted a cylinder with a radius of 1,000 and a height of 10. This could be an aquifer, for example. And this is the disk here, that cylinder. You can see that it's quite broad relative to its thickness, very thin disk. And then I put a polygon at x equals 0, y equals 0, z equals 0. That's one end of the polygon. And another end is at x equals 0, y equals 0, and z equals 10. So this is a line that extends along the axis of this cylinder. And you can see it. We can see the end of it. It's right there. And if we zoom in on that, there's the point that's the end of it. And if we make it transparent, you can see the line segment right there. That's making the upper surface transparent. Another way that we could do that, I'm going to make it opaque, and now I'm going to highlight the surface and then go to hide selected. And then view unhidden. One of the things when you use these hide and unhide, you hide an entity with this, but then sometimes it's confusing because things might not become hidden, or they may be difficult to see again. And you should go and check out these settings if you have problems with that, and also sometime reset is what you need. Okay, so we'll reset this, and we now are back to where we started. There's the geometry with this line source, what will be a line source down the center. So if we go to Darcy's law, we put this in just like last time. The hydraulic head around the outer edge is shown there. You can see that little purple band. There were 4 panels there, and all 4 were selected. They're shown here, and we select hydraulic head of 0. Now for the well here at the center, we used a boundary condition that's called a mass flux boundary condition. And so the mass flux, it was put in like this. I'll put in another one. So I right click, and this line entity is called an edge. So I select edges and then select mass flux right there. And once I've done that, then I'll select that point, bring it over there, and then I write the mass flux in there. Okay, so the way that you calculate the mass flux, I just disable that. I took Q, which is the volumetric flow rate, and I multiplied by 1,000. That's kilograms per cubic meter. That's to convert volume to mass. And then I divided by the length of 10, which is the length of the line that's representing the well. So that'll give you units of mass flux. Well, that'll give you the proper entity for this line source. These are the units that it's looking for, and you can see that it's a little bit different than the units of flux that we typically recognize as a entity per length squared per time. But nevertheless, the reason for that is because this is a line source that doesn't really have an area. So that's how you set it up, and go and run it using this study here that is set up with to run just that last model. And we do that, and if we take a look here at the plot that has all three of the results on it, you can see that it's hard to tell which one it is. So maybe we should go ahead and fix that. So let's put a legend on here in the lower right, and then we can turn the legend on for each one of these. So we have to go and label each one of these legend entries in order to have it show up and say something meaningful. It'll just number them, and it won't really be that useful unless we go in here and label it. Okay, so we see the results here, and we're seeing a kind of a similar pattern emerge for these numerical solutions. Okay, I've added one more model, so we've got a total of 4 models here. This one is also a 3D model, and let me just show you a slight variation in how to set it up. So I've already put the model in, I have some variables, but we need to put the geometry in. So before, with a 3D model, we put it in as a cylinder of 1,000 meter radius and a height of 10, and we'll do that here. So there's the aquifer. But now in the previous one we had the well be just a line element. We can do it a little bit differently. We can put in a cylinder that has a radius of 0.1 and a height of 10, and that appears right there. And now we'll say that that is the well. So let's take a look. We'll make it go transparent. So there it is. It has some finite thickness now in this case, and you can see it's a open cylinder. Well, actually, it's not an open cylinder yet. We have 2 cylinders superimposed on one another, but what we'll do is put in this thing called a Boolean Operation, and then we'll select both of these cylinders, cylinder 1 and cylinder 2, and now we can just simply write a formula that operates on these geometric entities. So we go cylinder 1 minus cylinder 2, and we run that, and what that does is cuts out the material that is representing the cylinder 1 geometry from, or it cuts out the cylinder 2 material from the cylinder 1 geometry. So let's see, we'll zoom in on the top of it here, and you can see that that's an open hole down in there. Okay, so that's the geometry, and now we need to set up the boundary conditions for it. So this is just a default. We'll put in the hydraulic head boundary, and we'll put in a inflow boundary. The hydraulic head boundary, we're going to zoom out, and we have to select these edges. For the inflow boundary, it's a little bit tricky to select them. We have to select these 4 edges, or 4 boundary surfaces. And so the way to do it, I think, that will work best is to highlight this upper surface and then remove it. So now we can simply click on these 4 surfaces directly. So we're hiding that upper surface, the top of the disk. So we select them, and then we just make the boundary flux. I think we had a variable that was called well flux that was calculating that. Okay, so we'll use a default mesh again. Let's take a look at what that gives us. And let's show the upper surface. So there it is, and I'm going to turn this transparency off. There's what it looks like on the upper surface. Okay, now we go ahead and run it. And after it runs, we're going to plot up the results. Okay, so the solution's done, and here is one view of the results. This shows the pressure along the bottom surface of the aquifer, and this is the pressure along the well. We've removed the upper surface, so we don't see that. If we include it, well, we need to go back up here to include it. Let's see. It looks like it'll take a little bit more to include, but what I want to show you is I want to plot the results of this analysis along with the rest of our data. So the previous 3D plot, we used this thing called a cut line 3D. This gives us the coordinates of the line that we plotted over. We can take a look at that. There's the coordinates along that line, and what it's doing is it's plotting the line, plotting the data that's in this data set called 3D V1. So what I want to do is make a plot that has the same coordinates, that plots over the same line, but uses a different data set, this new data set that I just developed in solution 10. So I'm just going to go here and duplicate this. So it's cut line 3D3, and I'm going to change the data set that it uses to solution 10. And now when I go here to, I guess it's this plot here that's been emerging, we can go and add another line graph and put in that cut line that we just created. And we go and select hydraulic head. And there it is. It's the pink line right there. So it's actually getting closer and closer to the analytical solution. One of the big things that we can do to change this error here is experiment around with the grid. If we make the grid finer, then this erratic behavior, you can see there's a point right there. This is probably one point in the finite element mesh, and this is another one. So it's this coarseness that gives us this kind of this error. And when we put the mesh in, when we put the well in as a 0.1 diameter hole, then it made the mesh around that smaller, and that's why this one is behaving more accurately. Anyway, that's an overview about how to set up different models, how to build these different geometries. They're all just very simple models, but it gives you an overview about how to get started.